Welcome to Exponential Functions, Growth, and Decay. Today's objective is to write and evaluate exponential expressions to model growth and decay situations. So how are we going to be experiencing growth and decay in exponential form? Well, first let's talk about growth. So let's start with the number 1, and let's double this number and see what happens to it. So if we doubled 1, we'd get 2. If we doubled 2, we'd get 4. If we doubled 4, we'd get 8, 16, 32, and so on and so on. Okay, notice how the increase happens every time. Here there was a plus 1. Here we had a plus 2. Here we had a plus 4, a plus 8, and a plus 16. The growth increased every time. So now let's look at decay. And now let's start with the number 1, but let's take half of each number and see if we notice any comparisons. So half of 1 is 1/2. Half of 1/2 is 1/4, 1/8, 1/16, 1/32. So very similar to the growth and decay that's happening with the numbers above. We're going to be studying growth and decay in this fashion, looking at the growth side of a function and the decay of the function as well. In this section, we're going to be studying exponential functions that look similar to this. So we're going to have a function with some constant base raised to an exponent. The base has to be greater than 0 and it can't be 1. So some examples. Would be, for example, f of x equals 3 to the x, or f of x equals 1/2 raised to the x. So in this section we're going to get used to seeing functions in this form. Let's start by looking at the parent function of f of x equals 2 raised to the x. Now I want to graph this, so I want to make an x and y table so we can get some points for our graph. So I'm going to pick x values of -2, -1, 0, 1, and 2. Now what I'm going to do is I'm just going to plug those x values into my function over here. So I'm going to have 2 raised to the -2, which we know is 1 over 2 squared, which is 1/4. And we'll keep doing that for each value. I'll make these lines here so we can see each one of these calculations clearly. So now we have next one, 2 raised to -1, which we know is 1 over 2. We have 2 raised to 0. We know anything raised to 0 is just 1. Then we have 2 raised to the 1, that's just 2. And then 2 raised to the 2 is 4. So let's plot these on our table so we can see what this graph looks like. So when x equals 2, y equals about 1/4. When x equals -1, y equals about 1/2. When x equals 0, y equals 1. When x equals 1, y equals 2. And when x equals 2, y equals 4. So we can see the curve that these exponential functions have. We can see the growth starts out small, and then after every step gets bigger and bigger and bigger. So when we look at these graphs, we want to also think about the domain and range. So if we remember, domain is all the possible x values and range is all the possible y values. In this example, there is no limit to the possible x values. We can plug in any x value into this function and we'll get another number. So our domain here is all real numbers. Now, is there a limit to the y values? Well, we see that there are no numbers here below this y equals 0 line. So we'll say that the range has to be greater than 0. So that was an example of a growth function. So let's get a definition for exponential growth and exponential decay functions. So a function of the form f of x equals a times b of x, with a being greater than 0 and b being greater than 1 is an exponential growth function. So, for example, a function such as 4 times 2 raised to the x, we would consider that a growth function. So these functions would look something like this. They would increasingly go up. Now a decay function is when b is less than 0 but greater than 1. So that same function, f of x, we can still have a be greater than 0, but then b would need to be, for example, 1 over 1/2 raised to the x. This would be a decay function. Let's take a look at two functions and tell whether they have growth or decay. So in this first function, there is no a value, but the b value is 1.5, or we can think of it as 3 over 2. Now we know the definition of exponential growth is any function where a is greater than 0 and b is greater than 1. Here b is greater than 1, so we consider this growth. Let's take a look at the next function. In the next function, we have an a value of 30 and a b value of 0.8. This value is less than 1 and greater than 0. So we say this is a decay. So the big thing is looking at the b values. The b values will tell you whether it's a growth or it's decay. In some scenarios, you're going to have to model growth or decay by a constant percent increase or decrease. And we can do that with the following formula. So if we have some function and we have an initial amount and we multiply that by 1 plus or minus r, and we raise that to the t. This is an example of another exponential growth or exponential decay. So this here is our final amount. This a here is our initial amount. Now the reason that I have the plus or minus here is because this can be either a growth or decay. So you have to read the problem to know whether to use a plus or minus. Now R stands for our rate of increase. So that'll be something like a percentage or a scale factor. And then T like most problems, stands for time. So this will be the number of time periods. But notice that this equation is still very similar to the ones we studied at the beginning of the section. It's just some base being raised to some variable that we don't know. So let's use that equation to determine the price of something as it increases exponentially over time. So Tony's buying a Les Paul guitar in 2000 for $1,200. So experts estimate that this value will increase by 14% per year. So we want to create an exponential growth model and then look at a graph to figure out when it's going to cost $60,000. So we're going to use our growth function of a times 1 plus r raised to the t. Now notice that I'm using plus here because this value is going to be increasing over time. If it was going to be decreasing, I would use a minus sign. So our function is going to look like this. A of t equals A's initial amount, so that's $12,000, times 1 plus the rate. Now the rate's 14%. We could write it in decimal form, so it's 0.14 raised to the t. Now we don't know what t is because they're asking us to find when, so we don't know that. So our final function is 12,000 times 1.14 raised to the t. Now figuring this out by hand right now is not what we want to do. So if you have a graphing calculator, we would punch this value in, and then by adjusting and zooming in, we'll see that we have a graph that looks similar to this. So here's the graph that we're looking at. Now, when we adjust and look for the appropriate y value of 60,000, we find that x equals about 12 years. So this is an example of using exponential growth functions to determine the price of something as it increases over time. So today we covered exponential growth and decay functions. Hope this video was helpful, and that'll be all for today. Thank you. Take care.